Okay. Derek, is there anything you want to go over with related rates before we do projectiles?
Yeah, so like the right side up problem.
Oh, whoops. Yeah, yeah.
So it refers to the height, the what is it? The H, right? So in the equation, the H refers to the air height.
Uh, okay. Could you give me a specific problem for this one?
Hold on. Okay, so it's a right side up cone.
Okay,
The
so this way?
radius,
Is it this way? Or
yeah,
okay.
yeah. So the radius is 5, and then the height is 10.
Okay. And
And then water's being poured into it at 2 feet cubed a second.
okay, so
And then you're trying to find dH over dt of the water.
the water. Okay, so why do you think that H refers to the the height of why do you think we don't just directly do the height of the water?
Because the height of the water is not referring to the height of the cone, which is what's being referred to.
Yeah, they're not. It's not a similar shape because if you look at the height of the water, it's it's a it looks like this, right? It has a flat top. That's a shape.
Yeah.
That's a lot more complicated to find the area for, right? So instead of doing that, what we do instead is we do a shrinking piece of air, right? So we do a shrinking piece of air.
Yeah.
Instead of a growing piece of water in this scenario. If it was the cone the other way, then we would do if it was a cone this way, then we would do shrinking, or we would do growing water because the water has a shape that's similar to the tank, right? So it's easy to find the height. Okay, so so how big is this all we should be given something that's changing, right?
Yeah. So water's being put into it at 2 feet cubed a second.
Okay, so so we have this shrinking air, right? I'll draw it right here for now. We have a shrinking piece of air, and uh, the volume of that piece of air, if the volume of the water is growing by a certain amount, then the volume of that piece of air is decreasing by the same amount. So how fast is the water being pumped in?
2 feet cubed a second.
So it's 2, right? And our units are feet cubed per second, right? So if dv dt, oh, it's -2 because we're doing shrinking air and not growing water, right? So the air is shrinking -2 feet cubed per second. So, and we know that the volume of a cone is 1/3 pi r squared times height. Okay. So what we want to do is we want to get since the air will be a similar shape, and this is also why we do air because it's a similar we do air because it's a similar shape, right? So we know that the ratio of the radius to the height will be the same for the shrinking air as it is for the overall tank. So we know that if r is equal to 10, so this is the tank, right? If r is equal to 10, or not r, if h is equal to 10 and r is equal to 5, that means h over r is equal to 10 over 5, which is 2, right? And we want to find the height of the water as it changes, right? So we want to turn this expression into volume in terms of height. That way, we get, when we take the derivative of everything with respect to time, we're left with dv dt and dh dt, and we can just find dh dt. So we can say h is equal to 2r, so r is equal to 1/2 h. If r is equal to 1/2 h, we plug that into here, so we get volume is equal to 1 h over 2 squared, so that's 1/12 pi h cubed, right? So, and we take the derivative with respect to what?
Time.
Yeah, time. So so it would be dv dt is equal to 3, and this is why it was so important when I did that derivative stuff to take derivatives with respect to something, because now you guys are doing related rates, and it's important to know that you're doing it with respect to time. You can also, I'll show you another way to do this by doing the derivative of the volume with respect to height. Actually, I don't know if you can do that. There's probably a way you can do it that way. I'll see, but let's do this first. 3 over 12 pi h squared times dh dt.
T. Yeah, and then
And
you want to find the dh over dt of the water when the height of the water is 3.
When the height of the water is
3
3.
feet.
So if the height of the water is
Yeah,
3
3
feet, then what's the height of the shrinking air?
7 feet.
7. So it's 7 squared over 12. So 3 times 49 times pi over 12. That becomes 1. That becomes 4. So it's 49 pi over 4 times dh dt is equal to -2. And so -8 over 49 pi is equal to dh dt. So that's the rate of that's how the height is changing for the shrinking air. So that means the height of our, I think this is called a okay, I don't know what that shape is called of the water. But anyways, so that means the height of the water is growing by the same amount. It's growing by 8 over 49 pi, and it's growing in feet per second. And the reason we know it's feet per second, yeah, it's because our units is in feet and seconds. So that's why we know it's feet per second. Okay. Does that make sense?
Isn't it feet per second cubed, though?
Feet per, no, because this is height. Height is one dimensional,
Oh, okay.
right? I'm trying to think. There's usually a way. Let me see. Yeah, so volume is equal to 1/3 pi r squared times height, right? If we replace these with their units of measurement, feet cubed per second is equal to, and we can get rid of all the constants, right? This is just like theoretical. So it's equal to r squared, so that's feet squared over second squared times oh shoot, there shouldn't be any seconds actually, because we're not doing with this we're not doing with respect to time. This is just in general. So volume is equal to feet cubed. R squared is feet squared because r is feet times feet. So that's how we know that's height. That's r squared. That's feet. And this expression holds true. So we know that h is in terms of feet. Okay. I think that's, unless you guys have another related rates or differentials, I think that's also what you guys are doing. If you have another one of those problems, shoot it right now before we get into projectiles. Otherwise, I think that's fine. Actually, do you guys want to see if there's a way to do this with the chain rule? I bet there is. Right? Let's do that actually. So if we have dv dt, and this is another way. That's why I showed you guys with the chain rule all those other times, is because another way you could do this. If we know dv dt, what can we multiply it with to get dh dt?
dh over dv.
Yeah. So the change in height with respect to velocity, or not velocity, with respect to volume, right? So this is, if the volume grows some amount, how much does the height grow, right? So this is the change in height with respect to volume. Anyway, okay, so we know, so we want to find dh dv at this specific moment in time that we're in. So if we know volume is equal to 1/3, and we knew that h over r is equal to 2, so r is equal to 1/2 h. So it's actually volume is equal to 1/4. Am I doing this right, or is it 1/3 times 1/4? Oh yeah, so 1/12 times h cubed pi times pi h cubed. There we go. Okay. And instead of taking the derivative with respect to time, we can take it with respect to, we can find dh dv, right? We can take the derivative of all this with respect to velocity. So dv is equal to 1/12 times 3 times pi times h squared times dh dv. This becomes 1, and this becomes 1/4. So 4 over pi times is equal to h squared dh dv. And what is h in this current moment in time? This is a shrinking cone, so it would be 7, yeah. So 49 times dh dv is equal to 4 over pi. If we divide by 49, we get 4 over 49 pi is equal to dh dv. So that's dh dv. Now we have to multiply it by dv dt, which is -2, right? So -2 times 4 over 49 pi. And remind me, I don't think anything cancels out there actually, so it becomes -8 over 49 pi. Is that what we got when we did it the other way? I don't remember. I think it was.
Yeah.
Okay.
Yeah,
so that's another way you can do it. You can do it with the chain rule. There's probably more ways to do this as well. But the point I'm trying to get across here is that you can solve a lot of these things just by taking the derivative with respect to something else, right? It doesn't have to be time. He showed you how to do it with time because it's the most widely applicable, right? But if you want to do it in a faster, or if you want to like check your answers, you could do it this way too. I'll see if there's any other way to do it. You could probably find. Actually, no. This is probably the best way to do it. Yeah. Okay. Now we can go to projectiles. I think, unless you guys have more questions, I'm fine with doing some more related rates. But I'm assuming you guys are chill until you guys get the test back. Is there any questions on the test that you like remember that you want me to do? I could try. If not, we can do projectiles. Does this sound good?
We can move on to projectiles.
Okay. All right.
Yeah.
Okay. What do you guys have for projectiles? I think for these kinds of problems, it's easier to just do an example instead of trying to teach you guys it conceptually first. So, shoot me a problem.
I sent one.
Oh, you did? Okay. Let me check. Okay. Hold up 1 second. Okay. A projectile is launched from the ground with an initial velocity. Okay, so we're assuming. Okay, all right, never mind. Okay, so one thing I would do for all projectile problems, no matter what, is it is to draw it out. And this isn't just for projectiles problems. I would do this with differentials too, and even or not differentials, related rates. Do it with differentials too. Just draw it out when possible, because it's gonna help you conceptualize everything, and it's just better. Like there's no reason not to draw these out. So anyways, a projectile is launched from the ground with an initial velocity. So you have a projectile. It's launched from the ground with an initial velocity of 96 feet per second at an angle of 40 degrees. Find the following. So actually, before we even do that, right? Let's just find everything we can about this. Okay, 1 second. Do you guys hear that noise too, or is it just me? Because it's kind of annoying.
I think. I don't hear anything.
Oh, okay. Oh, it went away.
Oh, I can hear it.
It went away from me, so I don't know. I guess Discord's being weird. But anyways, okay. So let's find let's put this under projectile, right? Let's find what's the acceleration in the y direction. Because actually before I do that, the fundamental thing about projectiles you need to know is that the x and y, for now at least, I'm not sure about air resistance, I haven't even learned that yet, but for now, the x and the y are separate. They don't affect each other. So that's why we can do these separately, because they don't affect each other. If a gun shot a bullet at like 100 miles per hour, it would still fall downwards at the same rate as if I just dropped the bullet. So, anyways, we're gonna do this in feet because it's easy. It's what Mr. Shao gave you, and it's the units that are given. So, what's the acceleration in feet per second? Or feet per second squared? Negative 32.
Feet per second squared.
And do you guys know why it's feet per second squared?
No.
Because acceleration is the derivative of, it's a derivative of velocity with respect to time, right? And our time in units is second, so it's feet per second times 1 over second, right? So it becomes feet per second squared. So that's why it's feet per second squared. Okay, so that's negative 32. And as I just said, the derivative of velocity is acceleration. So the antiderivative of acceleration is velocity. So how do you get the antiderivative of negative 32?
You set it up as equation.
I mean, for now, you guys are just taught to put a t in front of it, right? Right? Or you technically there's a t to the 0, right? So you bring the exponent up 1 and then divide by that exponent, right? So, so, and then you have to add a constant, right? Because if you take the derivative of something with a constant, the constant goes away. So if you take the antiderivative, there can be any constant there. We don't know yet, right? But in this case, we can figure it out. What's our initial, because we can split this vector up into its x and y components, and that's why you guys did vectors in pre-calc. So what's our y component here? What's the velocity, the initial velocity on the y value in the y?
96. Or 40.
Yeah, 96 sine 40 degrees. And also one thing I want to note is c isn't always your initial value. It's only our initial value here because we set, if we set t to 0, all that's left is c, so that means c has to be our value at t equals 0, right? But c isn't always your initial value. It's just because when you set t to 0, c is all that's left. So it has to be our initial value. But anyways, our x is 96 cosine 40 degrees. So that means our initial velocity now becomes, let me erase this. It becomes negative 32 t plus 96 sine 40 degrees. And this makes sense, right? Because every second that goes by, your velocity is going to go down negative 32 because that's gravity pulling you down. Every second it'll go down negative 32. The projectile won't go down 32 feet, but our velocity will go down 32 feet, or 32 feet per second. So that's our velocity. And then what's our height in terms of y? Because we know that height is the derivative of height is velocity. So what's velocity? Or what's our height?
Negative 6t squared plus 96 sine 42.
Yeah, because here the t is 1, so we make the exponent 2, and then we divide by 2. We bring it up 1, divide by that number. So negative sine 40 degrees times t. And do you guys understand why the derivative of height is velocity?
Yeah, because velocity is speed, and speed is based on the height over time.
Yeah, speed is based on our position over time, which is why I've actually been breaking my own rules here. I should be saying the derivative with respect to time of height is velocity, because it's the change over time of height. And then our acceleration is the change over time of velocity. So, that's our y value. That's our y stuff taken care of. Actually, there's also a plus c here, but what's our initial height of our projectile?
0.
So that goes away, because if you plug in t for 0, everything else goes away, so c has to be our initial value, and our initial value is 0. So now what's our acceleration on the x for now, since we're assuming there's no air resistance or anything?
96 cosine.
Actually, our acceleration is 0, because this never changes, right? Since we have no air resistance, our projectile's always moving to the right at the same speed. It's just the y value. It's just the y velocity that's changing. So if we take the antiderivative of this, our velocity with respect to x is just c, right? Because the derivative of any constant is 0. And what's our initial value here?
96 cosine 40.
Yeah, so that becomes 96 cosine 40 degrees. Does that make sense why the acceleration doesn't change? Because we're assuming there's no air resistance, so there's nothing acting against it. There's no reason for it to change.
So it's always just going to be 96 cosine 40 as the speed of, or the horizontal speed.
Well, the horizontal speed is always going to be our initial, it's going to be our initial launch value. It might not be this, right? Because imagine if it's on a moving car or something. Then you're going to have to take into account the moving car, right? But whatever speed it's initially launched at, that will be your velocity x. In this case, it's just 96 cosine 40. If it's stationary and you shoot it, it'll always just be, whatever cosine whatever. So that's that. Does that make sense? Did you guys do moving cars yet? Like shooting from a moving car or anything?
Yeah.
Okay. Yeah.
You didn't really.
Okay, that's fine then. He'll probably give you guys worksheets to do this week on that. But anyways, our height in terms of x will be the antiderivative of this, which is 96 cosine 40 degrees times t plus c. And what's our initial x position? We're assuming... Oh, and also another key thing I want to talk about here. We're just, for the sake of simplicity, we're pretending our projectile is at the origin in this specific scenario. It's easiest for us. But we could say this is like 20 degrees from our origin, right? And then we could say c is 20, right? Because if the axis is... Oh, and I don't know why it's doing that. Whoops. Anyways, if our axis, let's say, starts over here, right? And we say that this is 20, then when it lands, we subtract 20 from it anyways, right? So it doesn't matter where we put our origin as long as we're consistent. And so we actually, in physics scenarios like this, we call our origin the moment, and we just call it something different because it doesn't matter where we put the origin. Does it make sense why it doesn't matter where we put the origin?
Yeah.
Because we're going to have to account for it, right? If we change where the origin is, we're going to have to account for it in our final answer anyway. So we might as well put it somewhere convenient. And in this case, the most convenient thing is to have the projectile launch from the origin. So that means our initial, if we say that this is the origin, then c is 0. So that's all of our projectile expressions out of the way. So what was A? Could you say it out loud?
The maximum height attained by the projectile.
Okay. That maximum height taken by the projectile. Oh, the maximum height. Okay, yeah. So the maximum height. So if you think about it, right, when the projectile is being shot, something like that, right? The velocity is going to go from positive to negative and then hit the ground. So when the velocity is 0, right, it's going to not go up anymore, right? Because if it goes from positive, and this is where IVT comes in, right? If our velocity goes from positive to negative, and our velocity is continuous because this is a real world scenario, right? And it goes through 0, and we know it never comes back. I don't know why it keeps doing that. And we know it never comes back up, right? That means when it hits 0, that's going to be our maximum velocity. That's going to be the highest it's ever going to go from, because from then on it's just going to go downwards. So when the velocity, and that's where IVT comes in. That's why he taught you it at the beginning of the year. So when velocity is 0 of our velocity y is 0. When is it 0? It is 0 at t is equal to 96 sine 40 over 32. And I don't have my calculator on me, which is ironic because we're doing a projectiles unit, but most of this should work anyways, right? You can just put in your calculator and check yourself and see if it's right. But anyways, 96 sine 40 over 32. So that's when the velocity y is 0. So if we plug that in to our height y, right, we can know what the maximum height is going to be, because we know it's going to be its highest. It's going to peak when velocity y is 0 at that time. So we can plug that into our height and get, I'm going to call this t1, and I'm just going to say that's our answer. You can probably check that if you want to, but that should work fine. What's B?
How long do you think the projectile takes?
Okay, well, for this one, it hits the ground when our height y is equal to 0, right? So, I'm not gonna, is it okay if I just don't, like, solve these? Because you guys can just do this. He's gonna let you do this on your calculator. I'll just tell you.
Yeah.
Yeah, so to find when it hits the ground, you see where height y is 0. Generally, you'll get 2 answers because it starts from the ground at 0, right? And then it hits the ground. It hits the ground after a certain amount of time. So you want to get the answer that's farther out, obviously. And actually, if let's say your projectile launches from up here, right, with respect to your moment, you'll actually get an answer in the negative. And the reason you get that is because this is the reason you get it is because this is a quadratic and it has to have two answers, right? But this answer is meaningless because it's meaningless. I actually didn't think of a proper reason, but it's meaningless because our projectile starts getting shot from this point. So just keep that in mind. If you get a negative answer, that doesn't mean you're doing something incorrectly. So yeah. So our height, we check when our height is 0, and then we get the answer that's farther out. And you don't always get the answer that's farther out. You'll have to think about it. Like when, let's say it's being shot downwards this way, right? Then this will actually be our useless answer because we know that it's getting shot down in that direction, and that our parabola model is just creating an extra answer in that. And does that make sense?
Yeah.
Okay. And what is, let me check what C is. C is the maximum horizontal distance the projectile will cover. So the maximum horizontal distance the projectile will cover, well, when it hits the ground, it's not going to move anymore, right? So we just we know what time, since we know when the height is going to be. So when we solve for height y equals 0, right? When we do that, when we solve for that quadratic, we'll get the time when it hits the ground as well. So you just plug that into, where do you plug it into? You plug it into our height x, and when you plug it into our height x, you'll get how far it goes before it hits the ground, right before it hits the ground, or once it hits the ground. Okay, and then d is the impact velocity. Okay, so the impact velocity, right, when it hits the ground, you'll know the time it hits the ground, right? So you can find our velocity x and our velocity y, right? And just how we took this velocity vector and turned it into an x and y component, we can do the reverse, where if we have an x and y component, right, we can turn that back into a velocity vector. And our x and y component are going to look something like this, right? And you're going to have some theta. And you can do tangent inverse. You can do tangent inverse to find what theta is, right? And it's going to be some negative number. So let's say here in this case, I have no clue because I don't have a calculator, but let's say it's negative 16 degrees or something. Actually, you do know what it is in this case because this is just like a perfect parabola, right? You know that this is just going to be the negative of this over here, so it's going to be negative 40 degrees. Because we're considering this our origin. Does that make sense how I got negative 40?
Yeah.
Because, I mean, if it was being shot off of a building or something, then it would be different than our starting angle, but because it's being shot off the ground with no air resistance or anything, then it's just going to be a perfect parabola all the way through. So,
Wait, so how do you know that equals negative 40?
Okay, let me first explain what I'm about to explain, and then I'm going to go back to that. Is that okay? So, let's just say we get negative 40 degrees. You can do tangent inverse as well, right? And you'll get negative 40. And then you can do the Pythagorean theorem and get how the magnitude of the vector, how fast it's going, right? Well, okay, once you get negative 40, the reason he has you add 180 to it is just because it's honestly just how do I say this? It's because it's for convention. Because honestly, if you were to give your answer negative 40, your angle is negative 40, and your magnitude is whatever, right? If you were to give this, honestly, most people would take it. But Mr. Shao just wants you to add 180, right? So that your vector becomes. Let me do this in red. Your vector becomes this, right? This theta, but actually in this direction, right? So you'll add 180 and then make the magnitude negative. So it's actually the same vector, right? But it's just above the ground. Your theta is above the ground, which he likes. That's the only reason he has you add 180.
Wait, so you always add 180?
And make the magnitude negative, because if you add 180 and you don't make the magnitude negative, then all of a sudden it's going in this direction. That's not right. That's not correct. It's not going to go this way once it hits the ground, right? So you need to make the magnitude negative. So it's still going this way. So now your resultant vector, when you add 180 and make the magnitude negative, is this. Does that make sense? Or is there...
Yeah.
Okay, and then
it's the same thing.
Yeah, it's the same exact vector. It's literally just convention, and honestly, I think also another reason he has you do it is because he doesn't like negative angles, and the reason he doesn't want you to use negative angles is because in computers and stuff, like let's say I'll talk about making a video game, because I was just doing that, and it's something that came to my mind is let's say you have like a player, right, and you're capturing his rotation. The computer only does it from 0 to 360, right? And as soon as it crosses again, it doesn't, if it moves this way, it doesn't become negative, right? It just becomes like 358. So it's always positive. So he wants you to keep that habit of always being positive. If you ever apply it.
Have 360, like the range is 320.
Yeah, you can actually. You can do that too.
Okay. So how he wants it, he wants us to add 180 and then
Make it negative. He wants your vector to look like that. But you can, I guess you could always, you can still, um, oh, another reason, actually, this is also another reason. So, yes, you could add 360 and make the angle positive. Another reason is, if, if you do it the way Shai was doing it, how your vectors will look, it'll look like this, right? And then it'll look like this, and then it'll look like this, and then it will look like this, right? But it will, your point, your point will always be below your vector. Does that make sense? Or behind your point will always, the vector will always be behind your point, right? So you can, it just looks neater versus having, actually, okay, the more I'm thinking about it, honestly, it's just the way he likes it. There's not really, okay, wait, I just figured it out. This took a while. This took a while for me to, so the reason, oops, I'll just leave those there. The reason he has you make your vector look like this is because let's say he has you find the velocity at this point, right? Instead of the impact velocity, he has you find the velocity at this point. And if you do it the way he's doing it, you'll easily know whether it's going up or down simply if your magnitude is negative or positive, right? But if you have a negative angle, your magnitude would be positive and you'd have to think about it a little more to know whether it's going up or down.
Wait. So basically, you want to show that like it's going down.
A negative magnitude. Yeah. It's honestly it still doesn't make 100% sense because it doesn't even take like that much brain power to like figure it out otherwise. Like even with a positive velocity, it doesn't take that much brain power to figure out whether it's going up or down. But it's it's just a little bit easier if you have to. So that's why he makes you do that. So if the angle is negative, you add 180. Only if the angle is negative, right? Because if you add, let's say here, right, it's 40 degrees. If you add 180 and make it negative, then you're just doing the opposite of what Shai wants. Now it's going up, but the velocity is negative. So you're just confusing yourself. So you only do it if the angle is negative. You only add 180 and make it negative. Make the magnitude negative if the angle is negative, and it's just to make it easier for you to tell if it's up or down.
I was just confused with his answer key.
Mm-hmm.
He put like 96 feet per second, and then he didn't make it 96 negative, and then he just left that positive with 140.
140. I think that might be yeah, that sounds like a mistake to me. Because he might have meant and it's yeah, he did some weird cross. Like it's incorrect, but I think in his head he was doing a weird cross of having the vector be he was adding like 360 like you said, right, to make the angle positive, but in his head he added 180 and kept the velocity as is. So he did it wrong. I think you should ask him about that in class.
Oh,
Because it should become negative. Otherwise, what he's saying is that the object is going that way, which isn't true. Okay. So that that's a pretty basic projectiles problem. There are some more complicated ones. If you guys want me to do that, just give me 1 second. Okay, can I erase this? Or are you guys? Okay, so I'm gonna go get my calculator just so I can do it with you guys instead of so while I do that, while I go get my calculator, you guys should think up of good problems you want me to do. Fine. Give me something that's a little more complicated. That way I can show you guys a bit more conceptual stuff. All right, I'll be back. Just give me like 2 minutes. Okay, that didn't take as long as I thought it would. So, do you guys have any questions that you want me to do?
Yeah. Maybe a picture.
Oh, okay, yeah. Okay. Let me see. Okay. Do you have a? Is this? Do you have like the problem, or is this like something he did on?
Put an example we can use.
Okay. Um. Okay. You're gonna have to do your best to describe it for me. I can look at it and get the basics. So let me draw that out first. So you have a tank. Okay. So you have a tank going. So you have a tank. Let's call that A, right? And it's going. How many miles per hour? Is that 30?
Yeah, 30 miles per hour.
Okay, so it's going 30 miles per hour. And you have another tank over here going, I'll call that tank B, or it might be a car, I don't know. It's something, and I'll call that B, and it's moving how far? 10 miles per hour?
Yeah, 10 miles per
Okay, and we have a projectile going 200 feet per second. Okay, so a projectile is coming off of this at 200 feet per second at an angle of, is that 20 or 22? 22, I think, right? So that's 22.
Yeah, 22 degrees.
Okay, so before we do anything else, and I'm assuming we want to find the distance that makes it hit the car, right? So
Yeah.
so before anything else, we should figure out where our moment or our origin is going to be. So what do you think is the easiest origin that we can do?
Put it at where the projectiles come. Or at the tank.
At the tank, yeah. Yeah, I would do it at the tank. Yeah, and I mean the projectile's coming from the same place the tank is. So I would just do it at the tank. So that's our moment, right? Or that, yeah, so that's our axis. Those are our axes. So what do we want to do now? We want to first, these are in miles per hour, right? So we should probably convert these to um feet per second. So to convert them to feet per second, I honestly forgot the ratio, but I know that there are what 5,280 feet in a mile. So it's 30 miles per hour times 5,280 divided by 60. So we get it in feet per minute, and then divided by 60 again for feet per second. I'll do that on my calculator. Do you guys know what the ratio is? I'm assuming it's just 5,280 divided by 360, right?
Yeah. I just need to.
44 over 3, is that it?
Yeah. Oh no, I just got 44.
44. Wait, what do you mean? What's the ratio?
Just like 44 feet per second.
Oh, yeah, I'm saying the ratio you multiply it by is 44 over 3, right? Times 30.
Wait, let me try. I'm not sure about it.
Because I got 440 feet per second, not 44 feet per second. I might be doing... Here, I can just pull up. Alright, let's just pull up. Okay. How many miles per hour? 30? It is 44 feet per second, so I am doing something wrong. So Oh, you know what I was doing wrong? 60 times 60 is not 360. It is 3,600. So the easy ratio, if you want to, you take the miles per hour and multiply it by 22 over 15. And in this case, it gives you 44. So you're right. Yeah, it is 44, not 440. Okay. So I'm going to say this is 44 feet per second. And 10 miles per hour, so 10 times 22 over 15. That is 44 over 3 feet per second. Is that right? Is that right so far?
Yeah.
Okay. But we said our origin is here, right? So this car B is actually moving in a negative direction in terms of our moment. We could have, if you wanted to like be really wacky, you could have put the moment over here and made like a flipped axis, but like there's no reason to, so I wouldn't do that. But anyways, so that's negative 44 over 3 feet per second. So that's everything converted, and we're ready to start getting our equations. So we want to find the distance, and we're gonna call that d. Okay, so d question mark. Now, okay, so let's just do. Let's just find all of our equations for the projectile, right? So what's our velocity, or what's our acceleration for the y? Negative 32, right? Our velocity for the y is negative 32 t plus c. What's our initial value here? It's 200 sine 22. Our height in terms of y is negative 16 t squared plus 200 sine 22 times t plus our initial height, which in this case, we're assuming it's like inside the tank on the origin, because he didn't tell us if it was on top at a certain height, so it's plus 0. So I'll just not write that. And then our acceleration for the x is, now actually here's a unique question I want to ask you guys. Let's say the car that it's on, car A, was accelerating like 2 miles per hour, or 2 miles per hour squared, right? Would um would our projectile have an acceleration or not? No. Yeah, because as soon as it gets off, it'll shoot at the initial velocity. So all that will change is the initial velocity it gets shot at, because the tank will be at a different miles per hour depending on when it got shot, right? But it won't give the projectile an acceleration, right? Does that make sense?
Yeah.
So, like, let's say it was accelerating 1 feet per second. Our acceleration for the x would be 0, but our initial value would be, um, it would be, plus t, because we're saying this is going up 1 feet per second, so or let's say it goes up 2, and I know this is a bit convoluted, but let's say it's accelerating 2 feet per second, the car, right? Well, we would say this is 200 cosine 22 plus, let me write this better, plus t, right? T, let's call this T2, or actually we can just call it T1. And T1 would be the velocity of the car at the time it's getting shot out of or the missile is getting shot. The velocity of the car. And what's the velocity of the car? It would be 44 plus 2t, right? So that would go in there. So that's all that would change, right? Your initial velocity would go up. Actually, because this still. Oh, keep going. Yeah, keep. Yeah, that's still.
Wouldn't it, like, isn't it, like, really separate? Because, like, the car is accelerating. It's still on.
Yeah, it's still affecting, because technically all I said was the acceleration is 2 like the car, but that shouldn't be it. 44 plus 2t. We have 200 cosine 22, and we want to basically say at whatever value the car gets out, 44 plus 2t. Oh, you know what would change? We would treat this as a as a constant. That's the only thing that would change. So actually no, this is correct, right? But we would treat this as a constant. So that's why I didn't directly put it in, because we would treat this as a constant, and we when we find this would be x. When we find our height, it would be 200 cosine 22 plus t1 times t. Do you see how I treated it as a constant, right? Instead of saying t squared over 2. That's all that would change, right?
Yeah. So just change it to add.
Yeah. Okay. I think that should work. If he ever gives you a question like that, you can try what I tried and see if you get the right answer. Because I don't think Shio ever gives you a question like that, but I was just thinking if there was an acceleration, what you would do. I think that's what you would do. Anyways, so our height in terms of x is 200 cosine 22 times t plus our initial height in terms of x. And you know what we can do? We can make it so that oh shoot, you know what I forgot? Okay, I'm kind of all over the place, but 200 cosine 22 plus the velocity of the car. That's what I was talking about before. You might have to add to your initial velocity. It's 44 feet per second, right? There we go. So then this is 200 cosine 22 plus 44 t. And that should... Oh, because our car is moving 44 feet per second. That's the thing, right? When your projectile gets shot on top of a moving car, it inherits the velocity of your car at the specific moment it got shot. In this case, it has a constant velocity, so it'll get shot at that velocity. Plus that velocity, it'll have that velocity as well. Think about if you're like running and you throw a football. The football is gonna have whatever speed you threw it at plus the speed of you running. Yeah. So that's okay, so that's a projectile. Okay. So if that's our projectile, let me zoom out a little bit. Now we want to see where it can hit. We want to have it so it hits the car B, right? And wait, does it tell you how far they are apart initially, or actually it shouldn't tell you that. You don't need to know that actually. Okay. So let's say they are d1 feet apart at time equals 0, right? So and let's say d is the distance, is always the distance between them, right? So d is equal to distance, right? And we have d1, and that's the initial distance they're at. It would be d1 minus 44 plus 44 over 3 times t. Because every second they're going to get closer. This one's going to get closer 44 feet, and this one's going to get closer 44 over 3 feet. So that's our distance. I feel like there's something I'm missing here. Let's see. So you have that, and then do you know what the specific question was? Was it just find the distance they need to be? Oh, okay, yeah, okay. So this is okay. I'm overcomplicating this. Since we just want to find the distance that this car needs to be. All we need to do is see where this lands, and then see how much time it took to get there, and then we can account for it by moving the car. Because basically, we're allowed to move this car wherever we want before we, like, quote unquote, start the simulation. And that's where we want to see where we want the car to start. So let's see where this lands. When will height y be equal to 0? Do you have a calculator near you, or should I do it?
Like, 4.68 seconds.
4.68. Okay. So this is the one we want. We don't need this one because we know it starts at the origin. And we want to see, okay, at t equals 4.68, what is how far does our thing go? So if we plug this in here, we get, did you do it, or should I?
Yeah, I did it.
Okay.
It's HX is 1073.76.
Oh, okay, 1,000, wait, repeat that, 1,700.
1073.76.
Okay, and that's in feet. Okay, so it took 4.68 seconds for that projectile to go to this value, right? But this car is moving while the projectile's in the air, right? So we need to move this car back so that it's so that at 4.68 seconds it's at that spot, right? And if this car is moving 44 over 3 feet per second, we just need to move it 4.68 times 44 over 3 in this direction, right? And so 4.68 times 44 over 3. So that means this car needs to be back from the impact spot 68.64 feet plus the distance of the impact, or the distance from the origin to the impact, which is this. So if we add those two, we should get the answer.
Yeah.
Okay. Does that make sense how I got there?
Yeah. And if the car was going away, you subtract.
If the car was going away, yeah, because you're essentially, like, pretend there's a play button, right? You move all your components where you want it to, and then you press play and the simulation runs, right? So you want this, if the car is moving this direction, you want to compensate by moving it in that direction for the time that the projectile's in the air. Okay. There was something that always irked me. I'm trying to remember what when I was doing projectiles, and I think it was, oh, okay. So basically, another way you can think about this is, what if this car is stationary, right? And this is just moving 44 over 3 plus 44, right? Like, you would still get the same answer, because because essentially this distance is decreasing by this much every second, right? So if we want, we can have A stay still, and we can just have B move this amount. Or we could have A move 1, and we could have B move the rest. All we need to do is make sure that the distance between them decreases at the same rate, and we'll get the same impact. Does that make sense, or do you want to try it? You could probably try it by yourself. But yeah, if you want, if you ever have, like, if you ever run out of problems before the test, I would try just playing around. Like, okay, what if A stays still and we move B or something, right? I would just try around with those. Is there any other questions you want me to do?
No.
Okay, then I want to try, actually, wait. The one question I have is, if I make this move 1 feet per second and I make this move the rest, won't that affect the velocity of the projectile too? Or that's the only thing I'm concerned about is actually
So we can,
here. Yeah, do you want it? We can do it. Let's just you know what? Let's just do it right now. It won't take too long. So get ready to have your calculator out because I'm gonna ask you to do these. Okay, let me. So let's say um. Oh, actually, I don't want to erase the heights. The height stuff is gonna stay the same. So if this is moving 44 feet per second, right? So every few seconds it's moving 44 feet, right? And then it moves another 44 feet. And this is moving negative 44 over 3 feet per second. So every second it's moving 44 over 3. And then it keeps doing that, blah, blah, blah. We can have this stay still, and we can have this move instead. We can have this move both the distances instead. So we can have the car stay still, right? And then we can have this move 44 over 3 plus 44, right? Because the distance between them is still decreasing by the same amount. And you would still get the same answer. The one thing you would have to change, or the one thing you have to make the same, is you want to keep the projectile at the same velocity. So even though this is still, you still have to add that 30 or that 44 feet per second to the projectile. Does that make sense?
wait, but then wouldn't that change the whole the final thing?
Um. Wait. Keep going. Keep going.
If you keep the horizontal velocity the same, wouldn't that doesn't that count that you added 44 feet per second to the other to car B, so then you just repeated it without the 44 feet because A station.
Good question. Um. Yes. Actually, wait. So let's say. So if this stays stationary. Okay. Yeah. Actually, I see where that's actually wrong. Because I never actually tried it. I just assumed in my head that would work. Um. Yeah. Because and you know the reason why? It's because as soon as the projectile leaves the car basically becomes irrelevant, right? So it doesn't matter. This could be stay still already. It actually doesn't matter. All the only reason we need to know the speed of the car is we need to know how much velocity the projectile is going to inherit. So you're right, I think, yeah. So you have to do both. I did figure out, like, I can't think of it right now, but I did figure out a way to just like move all the velocity onto one of them and still get the same answer. But yeah, okay. I think that was for a different problem. Let me see. Let me think. Yeah, okay. Do you know when your projectiles test is?
I think it's next.
Okay, if it's next week, okay. Are you sure there's not any other questions? If not, we can end this. But if you have more questions, that's fine. Okay, cool. All right then. If I think about anything else with projectiles, like if I ever realize what I was so confused about back then, I will get back to you. If not, yeah, I think you should be good for this test. Um,
Right. Yeah. Thank you.
okay, yeah.